after, even after, yeah, the webinar is done. But then I think without any further ado, I will, yeah, give the name to my colleague Apostolos. So yeah, Apostolos, please.
Okay, sure. Okay, hope you can see my screen. Hello everyone, and welcome to this week's Senos Antenna Design webinar, where you will be introduced to the process behind geometry modeling and meshing of microstrip patch antennas with Senos, all in a brief and understandable manner. In the next webinar, we will go through antenna roles, solver properties, results, visualization / interpretation. So by then, you should have a somewhat good understanding of the antenna simulation workflow behind Senos. Of course, if you'd like to suggest topics for future webinars, feel free to write them in the chat. And if you have any questions, feel free to just type them out, and we will also have a dedicated Q&A at the end, by the way. And with that being said, let's just jump right into it by opening up Senos, the antenna design application. And as you can see, we've got the geometry, physics, and results sections. So in this webinar, we will focus on geometry, of course, and meshing. So let's open this up and save the case. For example, I can name it whatever I want. For example, webinar. And you can see FreeCAD is opening up. So in case you haven't familiarized yourself with FreeCAD before, this is basically the CAD interface that allows you to model your design however you wish. Later on, mesh it before sending it to Senos for the simulation. Now, FreeCAD is a versatile geometry editor toolset. You can see here a lot of options that allows you to add many shapes, including cube solids, spheres, cone solids, and many more. But in this example, let's just begin by loading a simple patch antenna from the component library. So we can click here on the component library icon at the top left. And for example, let's select the patch inset template, the patch inset component. So as you can see, our patch antenna has been implemented into the FreeCAD interface. And we can view around the geometry of the antenna in any angle and orientation by moving and rotating around the model. And you can also use this cube, by the way, to look at exact angles of interest. So now that we've got the basic design ready, by the way, you can also model this from scratch if you want. It's not super difficult. But to save some time and show you the important features behind FreeCAD and Senos, let's just import one example from the component library. So now that we've got the basic design ready, we'll have to optimize the parameters a little bit for our from the left panel here. Here, as you can see, patch inset parameters. And for example, let's increase the substrate length and width a little bit. Maybe to transform the radiation pattern a little bit, maybe perhaps increase the directivity. Let's, for example, say instead of 75, 77. And here, let's make this 80 millimeters as an example. And we can also adjust the dimensions of the patch width and length. For example, let's set the length to 42 millimeters and maybe 61, for example. And let's say I want to leave the parameters, the rest as is. So obviously this antenna will resonate now at a slightly lower frequency because the dimensions have been enlarged. So this whole process behind the parameterization, which you can do with any type of antenna, by the way, in FreeCAD, it encourages high precision modeling and ultimately the most accurate results for your antenna. Of course, depending on the frequency you wish your antenna to resonate at. Now that we've got, now that we put in our physical dimensions for our model, you can click out of the parameter spreadsheet, as I did, and view the model. And you can see that the dimensions have automatically been updated. So you don't have to click any buttons. It updates automatically. And you can see this on the 3D viewer interface. Finally, once our model is finished, it's time to actually mesh it. And we can directly apply mesh to our antenna by selecting everything from the list of objects on the left. So here we've got the substrate, the patch sketch, and the feed sketch at the bottom here. And just click the mesh icon. And as you can see, the sections icons have changed and are now intended for meshing rather than geometry modeling. So this is of course very important because it allows you to, because it lets us know that we're no longer in the geometry editor, we're actually in the meshing segment where we can actually apply the mesh and send the final design to Sanos. So let's click on the Create Mesh button here at the top, and just wait for the meshing procedure to finish. Of course, depending on how large your antenna is, or how many how fast your machine is, of course this can vary. You know how long it takes, and how complex your geometry is, and all this type of stuff. And you can see that the microstrip patch antenna has turned purple, and the mesh grid lines are clearly visible. So I can zoom in, I can pan around as usual. And this purple color is an indicator that the object of interest has been meshed successfully. If you didn't see, for example, this color, you might have done something wrong, or might have clicked something that you shouldn't have clicked, for example. And you'll notice that sometimes, particularly with feed lines and patch insets, the mesh is not as fine as it should be near the edges of the line. So I can zoom in here. Let me click off here. So maybe you can barely make out the sort of the inset. And let me, yeah, there we go. I can enable this to in case it's not obvious. We've only got two cells here. So we don't have a lot of mesh cells, and we have to make this part a little bit finer because you know, if you pass this to the simulator, and this is not just specific with the Xenos antenna design software, of course, it's this is in general the physics simulator. Like the solvers in general may struggle when you don't have a very fine mesh sometimes, especially at these edges here. So now, of course, depending on the frequency of your application, if the automatic mesh appears too coarse, you can always make it finer by selecting the substrate submesh in this example, in this case, and setting the characteristic length property to, for example, a little bit lower, like 1.5 millimeters. And once that's done, we can click on Recompute Mesh here. And at the top, yeah, here at the top, we can click this. And once this finishes, you'll notice that the mesh should look a bit finer. So let's wait for this to finish. And again, this can depend on what kind of machine you're running and what this value is set to. So as you can see here, it is a little bit finer. Let me bring this down. Yeah, as you can see here, now that I've put the sketch, I think you can note that there's actually four to five cells in this sort of line. Okay, so you might say that this is great. We've made it finer. We'll get more accurate results. And while this is true, you know, we have increased the entire mesh for the antenna when we only need to increase the resolution near the edges of the inset feed line. And this poses sort of a risk of significantly increasing the simulation runtime, which is obviously not something we favor. Obviously, we want our simulations to run as fast as possible and give as accurate results as possible at the same time. So there's actually a workaround for this. So there's like, here's a little trick to tackle this problem. First, let's set the characteristic length property back to the original value. I think it was around 0.480, just to show you that that it looks as before. But actually, let's actually just delete the mesh completely. So let's right-click on the group and click delete, and then enable this again. So now we're back. We're back to the geometry editor. It's like we never even clicked the mesh. So it's not like we've lost anything by going to the mesh or something. to the mesh section. And to make this trick work, to make this, because as I mentioned, we need only this part near the inset line to increase the mesh size, not the mesh size, to make it finer. The mesh size will actually be smaller. So let's click on the sketcher icon here, and click on create new sketch, and click OK. You'll notice that the view changed from 3D to 2D. This allows us to create two-dimensional sketches to apply to our model. And this is actually quite important because it enables us to create a sketch structure near the edges of the inset line here. And the mesh process will interpret it in a way that hints that this part has more physical content, meaning the mesh shell should be split accordingly in order to make this region finer. So let's create a line in the sketch by clicking here on this button at the top, and create two short lines near the edges of the inset feed line. So here is one line, and you can see it's placed, and let's add on more line right here. And now that our sketch is ready, we can exit out of the sketcher by clicking the close button. And as you can see, we have a new sketch here. So before we only had the patch sketch and the feed sketch, but now we've also got this sketch in the inset lines here in this region. So now that our redefined model is ready, let's once again select all of our objects from the panel on the left, and once again click on Mesh. Again, click Create Mesh because we deleted the older one, obviously. And now, if we open up the group of objects under Mesh and actually find the sketch that we've just created 1 minute ago, we can select it and click on Refine Mesh. So it is not Clip Mesh here. Refine Mesh for selected geometry. So it says it asks us for the mesh region. Now, of course, feel free to adjust the element size if you want very fine mesh cells. But let's leave it as is for now, and we can click create. But if you wanted to adjust it, you can do it without any issues. But let's just click create here to keep it simple. And finally, you might be wondering, well, I applied this change, but I don't see any difference in the inset region. We have to click on recompute mesh. So this recalculates the mesh given the input parameters. And as you can see now, the mesh is a lot finer here. Whereas before, if you recall, there were like only two cells, basically, two cells in this line between the inset feed line and the patch element. So right now, what we've done is we've created two sketch lines and have basically made this part a lot finer, which is obviously great because with the previous method, we had to make everything finer, which obviously not something we really want because it will take a lot longer to simulate. Whereas now, if you look around, everything else appears the same. We have not increased the mesh, for example. Let me highlight it here. We have not increased the mesh fineness here, but we've only touched this part. This is great because we have tackled two problems at the same time. We have made the simulation time a lot. We haven't made it faster, but we've made it more accurate with very, very little compromise in the simulation time. Because now the total simulation time just runs each and every cell here. But over here, this is the only part that really has to be fine. So this is basically the essentials of a meshing. And last but not least, you can just click on send mesh to, yeah, this is what it looks like without the sketches. You can click on send mesh to Xenos, and proceed to the simulation as usual, which, yeah, it says here message successfully, so no error, so that's obviously good. And then just select your antenna type and so on, which we will look at in the next webinar most likely. So, and with that, this is the basic, the fundamentals behind geometry modeling and meshing. And I'd like to thank you all for attending this webinar on patch geometry and meshing with Sanos, and hope to see you all in the next ones, which would likely involve further in-depth simulation properties, solver parameters, microstrip substrate material selection, result visualization, and more. And of course, if you've got any questions, feel free to ask. And if there are any topics you'd like to suggest for our next meetings, go ahead and propose freely.
Thank you, Apostolos. Thank you for the very nice presentation. Yeah, so as Apostolos just said, so this was the webinar, sort of an introductory webinar into patch antenna smashing. As you saw, the geometry was not very complex, and I do believe that a lot of you who are attending the webinar currently have already had some experience with Sanos. So if you have some specific questions, or if you would like to discuss any specific topics that you are interested, or share any specific problems that you encountered, then please, right now is the best time to do that. Currently, we are going into the Q&A of the webinar. So if anyone has anything to say, to comment, to ask, please go ahead.
Okay, I think Simon has asked a question in the chat. It may
Yes.
be a little early to say, but can you talk about how we would put sketches inside 3D parts such as buried microstrip? Okay, so I think by buried microstrip, what Simon means is, for example, maybe not aperture coupled, but maybe proximity fed antennas. So in case someone is not familiar with proximity fed antennas, you have essentially 3 layers. You have the bottom layer, which is usually made from copper, just the ground plane. Then you have a substrate, and then you have the feed line, the actual feed line of the antenna. And once again, you have substrate and then the patch element. So there's not direct contact between the feed line and the patch element, but it is very close. For example, this is why it's called proximity fed, because the proximity is close. So how would you do this? I think the easiest way would be to essentially build it like you would build a regular template, like not template. I mean a regular patch antenna, and simply create another sort of patch antenna and place it on top. So the model should work just fine. You just create the sketch first to not be able to like overlap and then not be able to work on it very easily. So once you've once you've built the sketches on each layer, you can then mesh it as usual and just mesh it and then just go to Sinus. So in the roles that you're asking, Simon, I don't know if it is that difficult to assign roles, because I believe you can actually click on the eye icon, which sort of disables or sort of hides the upper layer, I believe. So I think you can just select it like that. Other than that, perhaps you could also, maybe another alternative would be to maybe FreeCAD. You can look into FreeCAD to see how exactly this face is defined. Yeah, this should actually work. I think you can actually see like which face is defined, and then go into the roles and select the corresponding one. So maybe try something like this, and of course, if you're facing any issues, reach out and we'll definitely look into it. Or if it's not super convenient, we can definitely give it a shot to make it even simpler.
Yeah, I exactly agree with Apostolos that there is a possibility to hide geometries when you define roles. I think both 3D and 2D, but I'm currently opening Xenos on my side as well, just to double check. But yeah, there should be a possibility to just hide the geometry that is in front of you, and in that way you can take a look inside your setup, and then you can select the sketch that you have put inside your geometry. Okay, yes, Simon, thank you very much about the question. This is indeed an interesting one, and we do intend to dedicate one webinar specifically about roles, how to select them, how to add them, and in general, how to work with them. So this will definitely be one of the topics that we will include in that webinar. So yeah, again, thank you. Does anyone else has anything to ask us, or any comments or anything?
Sorry, it's Gavin here. I've been trying a number of different methods. I mean, I've got a patch that I've been trying to do, and I've stepped back from that because I've had a lot of difficulty trying to get meshes for that patch. And so then I've just gone back to a simple quarter wave antenna, and even that's been difficult to get to simulate. I got one simulation to work, and since I'm new to this simulation, it's sort of interesting, but I think it's more to do with how you do the port on a quarter wave. So you understand a quarter wave, just a standard quarter wave element out the top, and then I've got three ground elements on it to give you a closest enough to 50 ohm match on the from the feed. And so I'm just trying to understand that when you define, say, a port, and if I look at your example for the dipole antenna, it's got a particular length. Does it matter how long the feed length is in the middle of, or the port is in the middle of the dipole? That seems to be affecting. So on the quarter wave, I made it 4 millimeters and it worked. It simulated, but it gave me the wrong impedance. Wrong impedance, and it was also the wrong frequency for that length. And then I've tried to make it 0.1, and now it can't even pick up the right boundaries with that size port. So I'm just sort of struggling to understand that, and also just how you even, if you get any overlap, I've discovered in any of the element parts, it won't even mesh then because it says there's element overlaps. So is there rules as to when you've got a shape that's not normal, like if you haven't got a straight piece of wire, but you've got, in fact, I've got these three elementals that I want to come off at 45 degrees off of some solid mass, how would you best define that so that it can be meshed? And what I ended up with is a hexagon shape, and then taken three metal pieces of wire that are actually rectangular in shape coming off that hexagon, and then the element itself out the top is circular but a different diameter. I mean, I've asked lots of questions there, but maybe it's more about the port issue, I think, than the actual element. I understand that you can't have overlapping element, in the design, nothing can be overlapping, I've discovered, which makes sense. When you go to mesh, it can't work out where the mesh is. So can you just make some comments on port assignments?
Yeah, sure. Yeah, that's those are very fair questions. So as for the quarter wave antenna, what I would do is simply use a coaxial port, actually. This is probably the best way to handle this type of antenna. I don't think a balun is commonly placed there. And I'm not talking about impedance tuning balance. I'm talking about one-to-one balance. So coaxial port would probably work there. As for the meshing for wire antennas in general, what we've noticed is that sometimes if the ratio between the wire length to the wire diameter is very high, it can get a little bit tricky for the mesh to sort of apply a good good mesh. because it ends up like in order to sort of maintain the shape of each cell, of each mesh cell, it may end up creating a very large mesh. So this might be a little bit troubling sometimes, but it's not always the main issue. For example, in general, it can be resolved. It's not like that bad. So for the quarter wave antenna, I would go with coaxial port. And first of all, test this. For example, you mentioned that with the mesh, I think you passed to the mesh stage, but could not properly define the port. So I would recommend trying coaxial port. And by the way, we've also got in the components library, we've also got an Sma connector, which should help you directly just plug it in to the quarter wave antenna, and then define the port there as coaxial. So it would be similar to how you would excite, to how you would stimulate a horn antenna, for example, with the connector. One more question you asked is the overlapping. So the overlapping, it's not like I wouldn't consider it a bug necessarily, because in fact I sometimes consider it a good thing, because the software warns you that you actually place something that is actually overlapping, which obviously doesn't make a lot of sense in the real world, and it can sometimes confuse the solver a little bit, especially if you've defined different sort of materials between the two objects. One way to tackle this is to use the FreeCAD tools. For example, if you don't really want to manually adjust every little parameter in order to make it so it almost tangents the other object, one way to do this is, for example, to fuse the objects together in FreeCAD, or group them, or apply some Boolean operation in any way you like to sort of separate them in a sort of natural way. And then just mesh it as usual, and it shouldn't have any issues. So I hope this helps a little bit.
Yeah,
thank you.
I completely agree with what Apostolos said, especially about the meshing. So we know that the meshing not always works as we would want it to be, and we are actually working every day to improve the meshing, because we know that for some antenna types and for some geometries, especially if we talk like about thin wires, it could be a little bit troublesome. But regarding everything else, I hope Apostolos covered, if not everything, that then most of the concerns that you gaming had.
Okay, thank you. I think some of that may be related to thin wire. So the ratio of my element diameter to length was quite small. I think I had a 1 millimeter diameter and a 31 millimeter element, which should be a quarter wave for 2.4 gigs. And that's what I've made physically in the past, and I know they work. But if I have to sim it with a bigger diameter, that's fine as well. I was just more trying to understand that they were more a learning, because I'm trying to build this patch and I can't get that to work. And I was just trying to understand the meshing, and that gave me a good path to doing the meshing methodology, because, I know how it should work. And then, so I'll give that a go. I still don't know how to do my patch yet, but I think I have to put 3 ports and get rid of my hybrid network for feeding, and just feed it with 3 ports that are actually separated in phase, and that will be easier than trying to do the feed on the actual product.
Mm-hmm.
Yeah, maybe that should help actually.
Yeah. Regarding wire diameters, just improve them, increase the diameter a little bit, and see if the measure works. If not, then maybe reach us out, and we will take a look. And regarding templates, actually the same. If you still have some problems, we are here for most of the day, most of the daytime. So you can reach us out via built-in chat within Xenos software itself. So if you have any questions, please reach out to us, send us the case, and we will happily take a look. Okay.
Simon also adds that. Simon also adds that increase in diameter wire might help. By the way, I also thought I remember that maybe for this kind of antenna, the wire diameter doesn't really I don't think it affects the resonance of the antenna that much or the radiation pattern, because the electric field forms between the core conductor and sort of the ground plane. So most of the current, I guess, would sort of form on the surface of the wire of the ground. What would make a bit stronger difference would be the core, like the element going sort of upwards, not the ground, the core conductor. So I don't think you will see much difference actually if you increase the diameters of the ground plane wires. So that's my last comment.
Yeah, thank you. Does anyone else has something to add or ask to us? All right, then if no further questions follows, then thank you for joining for today's webinar. As I said, this webinar is recorded and we will upload the content that we discussed later on YouTube, on our YouTube channel. So if you want to revisit what we discussed today, be our guest. Besides that, as you know, you can reach us directly within chat, built in Xenos, or just reach out to us via email, and we'll be happy to chat with you and help with any problems that you have. Thank you for joining, and yeah, see you then the next time in the next webinar. Have a nice day. Bye-bye.
Bye, all.
Bye.